All right, second section in integer operations, 5.2, is multiplication and division of integers. And the models you see are going to look very similar to the models before. The interpretation or how we work with them are going to be a little bit different. Now on this one we have -4 times -3. And so I want to show you what it looks like for the chip model and the equivalent to the charged field model for this description. So let me write out what these are actually telling us, and then I'll show you how to do a picture that makes it work like a visual for what's happening. This -4 right here says to remove or to take away 4 groups. Okay, so -4, remove 4. Okay, remove 4 groups. And I could, well, I'll say that in a second. The -3 right here says of 3, we'll say red chips. Those are the negative chips. Right? Those chips right there. So we're going to start the circle. And when we start the circle, there is nothing inside of my circle. Okay? It's a big fat whopping 0. Nothing's in there. What I'm going to do is I'm going to put red chips and black chips in pairs so it stays a value of 0 inside my circle. Is everybody good with that so far? Okay, so now you know how many we probably need to add in here because you've worked with this kind of a problem before, but maybe not from the picture point of view. So I'm going to add in here, I'll make them a little bit smaller so that I have a little bit more space. I'm going to add into here barely fit them all, 12 of them, and I'll show you why in a minute. And I'm going to add in there to accompany those 12 of them, 12 red. This is the number 0, right? 12 red chips, 12 black chips. We can compare them one at a time. They add to 0. Everybody good with that? Okay, this is the number 0. But now I actually have inside of my circle the red chips that I want to remove. I need to remove 4 groups of 3 red chips. So let me remove one group of 3 red chips. There's one group of 3 red chips and it's removed. Here's another group of 3 red chips that gets removed. Here's a group of 3 red chips that I'm going to remove, and here's my last group of 3 red chips that I'm going to remove, and I did in fact remove 4 groups of 3 red chips. Now if I had any red chips still in there, like I just put in too many to start with, I could just take red chip, black chip, cancel out what's extra that I don't need, okay? So if there's extra in there, it doesn't hurt anything. But the result then, after I've removed the 12, in this case red chips, is that I have 5 black chips in my, 12 black chips in my circle, right? Which means that the answer then is what? 12, and it's actually positive 12, isn't it? Whoops. I have 12 black chips. I do the same thing with the charged fields model. It's not any different. I just use pluses and minuses instead of red chips and black chips. So we have our circle. And we have our screen that... Alright, so we have our circle, and we've got in it, well, we've got to put in it anyway, enough of the pluses and minuses to make this work. So I'm going to put in extra this time just so you can see what would really look like if you had extra. So let's say a child were working this. They don't know that they've got to inherently put 12 of these things in for some reason, because you and I both know that. But there's 10, 12, 13. Let's say they put in 15 pluses and 15 minuses, because in reality they can put in as many pluses and minuses as they want as long as they put in the same number of them, right? Okay, I think I got enough in there. Then what I'm supposed to do is I'm supposed to remove 4 groups of 3 red chips. Or likewise, you could say that I'm supposed to remove 3 groups of 4 red chips, and that would work too. The interpretation's commutative, right? So it doesn't matter which way we look at it. But I need to remove 4 groups of 3. So here's one group of 3. Here's 2 groups of 3. Here's 3 groups of 3. And here's 4 groups of 3. There's still some red chips that didn't get removed, so you don't want to go over the board here. You're not trying to remove extras that are there. But if you notice then that these 3 red chips would cancel with 3 black chips, then you can do that just like we did in the last section. There's 3 blacks with 3 reds. They kind of cancel each other out. They're opposite operations. So the result then is 12 black pluses from where we originally had far more pluses and minuses in there, and you get the number 12. Okay, are you ready for the number line model? Word of caution, also, I'm not a huge fan of the number line model for multiplication, but I'll show you how it works. It works a little bit better, I think, than the subtraction, but it still feels very awkward. Maybe in some ways more awkward. Let me show you. All right, so this -4 here is moving left 4 at a time. And you're probably okay with that, sort of like you're jumping, right? You're jumping across, 4-foot jumps or whatever. You're making these 4-foot jumps left. This part's the part that's awkward. This -3 is at a time starting 3 hours ago. So the fact that it's starting 3 hours ago instead of 3 hours into the future is because it's a negative. It's something happened in the past. You did it 3 hours ago. So the question is actually, where did I start? So in essence, what you're doing is you're going to create a number line, and you're going to create a number line without putting a 0 on it. In fact, you know what? I'll just use the line that's on my screen. How's that? And you're starting right here somewhere. This is where you're starting. I'll just mark it X as an X marks the spot, not X as in an X value, okay? And you're supposed to move 4 left. Sorry, you're supposed to move left 4 times. No, I said it right the first time. You're supposed to move 4 left, and you're supposed to do it 3 times because it says 3 hours ago. So we're going to make 4 left, 1, 2, 3, 4. That's my jump of length 4, 1 time. My jump of length 4, 2 times. My jump of length 4, 3 times. Okay, is everybody good with that? Move left 4 times. Wherever I end at 0. Now I call that 0. And I go back then and I say, okay, well then where did I start? You can actually count, multiply however you think about it, and what do you end up having, where did you end up having started at? 12. So the answer is 12. I'm not a fan of that. It feels so awkward. But that's how you think about it. That is the proper number line model for this particular description. You're talking about what happened in the past. They do a pretty decent one in your homework or group work, I can't remember which one it is, that actually shows this idea working out very well. I mean, it actually makes sense in terms of that particular problem. When you get there, I think you'll know what it is. But it has something to do with enrollment trends or something like that in the past and how many students used to be at a school or something like this. All right, let's look at integer multiplication as a definition. Integer multiplication, or at least some features of it, say the following. If A is less than A is less than 0, and B is less than 0, that is, if you have 2 negative numbers, then when you multiply them, A times B, you end up getting the absolute value of A, or its equivalent, I should say it that way, to the absolute value of A times the absolute value of B. Right? I mean, like you multiply a negative times a negative and you get a positive number. So that's where those absolute values are sort of hearkening us to think about. However, the other one looks a little bit different. It says if A is less than 0 and B is greater than 0, or if A is greater than 0 and B is less than 0. In other words, if one of them is negative and one of them is positive. It's a fancy way of saying that. One positive, one negative, and you multiply them, you will get a negative number. Kind of feel like I could have written that in words better, don't you? A positive times a positive is a negative times a negative is a positive, and a positive times a negative is a negative. That's all that's saying. Okay? Let's talk about the properties of integer multiplication. You've seen most of these before. The first one is the closure property. I know some of you are still struggling with the idea of closure, so let me reiterate again how closure works. Closure is the idea that if you take any two numbers from a described set, in this case it is the set of integers, okay, positive and negative whole numbers. If I take any two integers and I multiply them, a times b, I will get another number in that set, in this case in the set of integers. So ab is a unique integer. Okay. Right? I can't multiply two integers and get a fraction. I don't multiply two integers and get a square root. It's not possible. I multiply an integer times another integer and I get another integer. Next one, the commutative property of multiplication. You guys remember commutative. That's one that people tend to remember. What's the deal with that one? Switch in order. So if I have AB, it's going to equal BA. You bet. Associative property. That one has to do with parentheses. And it's not just parentheses, but it's what's inside of the parentheses, right? So if I have 3 A, B, C, A, B, C, and the associative property holds, it means I could group the first two in the parenthesis or the second two in parenthesis, and I would have the same result. And of course, from order of operations in the last section, you would work inside of the parentheses before you multiply by the outside value of the parentheses. So there really is an innate difference in what you're doing. You are multiplying different values together when you use the associative property. Okay, we have a few more. Identity property of integers. Some of you are still working on yellow tests and talked about identity things. There is an identity element. One is the unique identity or value, or however you want to describe it. It's the unique identity such that, or you could say because that, or because of the fact that 1 times any number is equal to that same number times 1 is equal to the number A. That was awful. Let's try that again. There we go. The identity element is an element such that when you multiply, because we're talking about multiplication in this case, multiply by the number, that's the identity, the number 1, it doesn't change what you were working with. Distributive property, we've seen that before too. That's a combination property about multiplication and addition. It says that if you have A times B plus C, what will that equal? A plus B times A plus C. And because of all of this commutative identity, or commutative ideas, if I had B plus C times the A, I could do the same thing. I'll keep it in the same order that it's actually written. So this is actually BA plus CA. But of course we could switch the BA and the CA rounds that actually looked like it was the same because that's commutative. We have that property. We have one more multiplication property. Again, you've seen this before as well. 0 is the unique integer that does what? What does 0 do that nothing else does? It will 0, right? It zeroes everything out. No matter what A value you had to start with, when you multiply it by 0, you get 0. And of course it works on either side. A times 0 or 0 times A, both of them are 0. This is the unique integer that does that. Okay, we'll do one more slide and then we'll pause for today. We're going to identify the integer property that's being used or illustrated in the problem. So what's the first one? That says negative 2 times 3 is an element of the integers. Remember how to read those? We did that back in chapter 2. That is closure. How about the second one? Negative 4 times 0 equals 0. That's the zero property. How about the next one? Negative 2 times 3 plus 4 equals negative 2 times 3 plus negative 2 times 4. That is distributive. And the last one, negative 2 times 3 equals 3 times negative 2. That is commutative.